It's like another one which deals with change in volume with change in temperature. This problem says compute, this is 19.10, and it says compute the density of iron at 700 degrees C given that the room temperature density is 7.870 gram per cubic centimeter, and it says that we can approximate the volumetric thermal coefficient of expansion as 3 times the linear, and that's because the linear is coming from your textbook in the table, and that is, let's see if we can find that here. It is 11.8 times 10 to the minus 6 inverse degrees Celsius. Okay, so for this we want to know the change in the density, or we want to know what the density is, which means we want to know the mass per volume, and if we have an initial mass per volume, what we're going to do is we're just going to take that and approximate that the mass doesn't change. So let's say we're given a cubic centimeter of iron. Well, then that means that it has a volume, which I'm going to call V0, of V0 mass of 7.870 grams. So this is going to be our V0. So now if you have a V0, we can use delta V over V0 is equal to alpha V delta T. That delta V is Vf minus V0. And what we want to do is we want to find, sorry, not V0, we want to find Vf. And if we have Vf, then we can put that in with our mass, which is going to be constant as we heat it up, and find the new density. This delta T is Tf minus Ti, the initial. This is room temperature. And this is 700 degrees C. So, let's take and work with this a little bit. Vf minus V0 over V0 is equal to alpha V delta T. We can use 3 alpha L here, move this over so we get Vf is equal to V0 3 alpha L delta T plus V0. And now that's known, that's known, that's known, and that's known, which is going to give us, Vf is equal to 1.02471 cubic centimeter, and that is compared to our V0, which was 1. So heating it up from room temperature to 700 degrees C gives us a slight change in the volume, and that means that rho at 700 degrees C is equal to 7.870 gram divided by 1.02471 2471 centimeter cubed, which is equal to 7.68 gram per centimeter cubed, keeping 3 significant figures, which is slightly smaller than the initial, which was 7.87 gram per cubic centimeter. Okay. Next, let's look at problem 19.11. And this problem is kind of neat. It asks you to look at 2 changes in the volume. For one, you have thermal expansion, and that's what we looked at in the previous problem. But second, when we heat it up, we create vacancies, and those vacancies displace mass, and therefore it causes the volume to expand. So part A says determine the density due to thermal expansion, and part B says take it and recalculate, but look at what happens when we introduce vacancies. And for this, we have to know the enthalpy of vacancy formation, or activation energy for vacancy formation. And we're also again given that the volumetric coefficient of thermal expansion is approximately 3 times the linear. This component to the problem, if you remember, it has to do with an Arrhenius-like relation, because we're talking about the energy to create vacancies, which is why we have this activation energy. So let's go back and let's just start from the first part, part A. So part A, this problem looks absolutely identical to the previous problem, right? That previous problem in which I'm trying to find it. Funny, I set down a piece of paper and lose it almost immediately. This problem, right? That was our solution last time. So let's keep that equation. V0, 3 alpha L delta T plus V0. So we have that. We're also going to work here from the assumption that, well, it's gold, and it has a density of 19.320 gram per centimeter cubed, which means that if you take V0 to be, excuse me, 1 centimeter cubed, then the mass is 19.320 gram. And with that, you substitute into there alpha L for this problem. Let's see if I can find that. Is 14.2 times 10 to the minus 6 inverse degrees centigrade. That's from table 19.1. And now delta T is 800 degrees C. So that's 800 degrees C minus 25 degrees C. And given that, we wind up with VF equal to 1.03323 cubic centimeter, which means rho at 800, taking into account thermal expansion only, is 19.320 divided by 1.03323 gram per cubic centimeter, or 18.699 gram per cubic centimeter, which is around 18.7 gram per cubic centimeter, keeping three significant figures, which is a little bit, well, considerably smaller than the initial, which was 19.3. Okay, let's work on problem B now, and we'll keep this kind of as our side problem. Now, the next part of this problem has to do with how many vacancies are added. So before we can determine the number of vacancies per volume, we have to determine the number of atoms per volume. Right? So if we have, we want the atom per cubic centimeter. Well, we have the density, so we have gram per cubic centimeter, but we've got to get rid of those grams somehow. So we can divide by gram per mole. That's the atomic mass. That's the density. So here we're getting rid of the grams, but we still have this molar quantity we gotta get rid of, which means atom per mole. Moles go away. This is Avogadro's number, atom per mole. So that means that the number of atoms per volume are going to be the density of gold times Avogadro's number divided by the atomic mass of gold. So units are once again, for now and forever and for all time, your friend. This is the number of atoms per cubic volume. Okay, great. Substituting in our values, this gives us 5.717 times 10 to the 22 atom per cubic centimeter. Okay, we got that. Now, the place we're going to use this is we're going to go back and remember from chapter 4 when we talked about defects, that the number of vacancies or defects in general scales as, well, it's an Arrhenius relationship, and in this case it's going to scale as the number of atoms per volume this is the number of vacancies per cubic centimeter, this is the number of atoms per cubic centimeter. This is exponential of negative QV over KT. why K and not G? Well, the reason for that is that we are given vacancy formation energy of electron volt per atom. And the difference between the Boltzmann constant and the gas constant is the gas constant gives you energy per mole, and if you have energy per atom or energy per event, then you use the Gibbs, you use the Boltzmann constant. So that's why we have Boltzmann constant in there. So we now have this. That QV was given as 0.98 EV per atom. T, this is 800. And K, it's a Boltzmann constant, which I don't remember offhand. This is, see, let me look it up. I got it written down. It's 8.62 times 10 to the minus 5 plus 273. K, this is 8.62 times 10 to the minus 5. That's EV per K. So we got all that, which gives us the number of vacancies per volume, 1.431 times 10 to the 18 vacancy per cubic centimeter. Okay, so far so good. I should remove this over here. And the next step is we've got vacancies per cubic centimeter. We'd like to know how many vacancies per cell. So let me for the volume of unit cell. This is going to be number of atoms per cell times the gram per mole, the atomic mass, divided by gram per cubic centimeter, atom per mole. Moles go away, grams go away, atoms go away. This is going to be centimeter cubed per cell. So this is 4, we know that. This is 196.97 gram per mole. This is the atomic mass. This is the density, which we calculated to be 18.699. This is after taking into account thermal expansion. And this is Avogadro's number, 6.02 times 10 to the positive 23, which gives 6.997 times 10 to the negative 23 centimeter cubed per unit cell. VC. So the number of vacancies per unit cell, that's going to be the fraction of vacancies, the vacancy per cubic centimeter, I should say. So the density of vacancies multiplied by centimeter cubed per cell to get vacancy per cell. And this is from here 1.431 times 10 to the 18, and this is 6.997. 7 times 10 to the negative 23. Vacancy per cell is 1.001 times 10 to the minus 4 minus 4. Vacancy per cell, which means atoms per cell, is now equal to 4 minus 1.001 times 10 to the minus 4, or 3.9998 per atom per unit cell. And if you remember back from chapter 3, we had this equation. The density, the theoretical density, was the number of atoms per cell times the atomic mass per cell times the volume per cell times Avogadro's number. So now N is not 4 but 3.99989. AAU is still 196.97. VC is 6.997 times 10 to the minus 23 centimeter cubed per cell, and Na is 6.02 times 10 to the 23 atom per mole. This is atom per cell. Atoms go away. This is gram per mole. Moles go away. Inverse cells go away, leaving us with grams per cubic centimeter. So rho is equal to 18.698 gram per cubic centimeter. So let's go back and compare that to our original calculation. So we originally calculated that the thermal coefficient of expansion would result in the density changing from 19.32 to 18.699. And then if on top of that we add vacancies, it changes from 18.699 to 18.698. The difference is out in the third decimal place, which means that the vacancies are really, relatively a small contributor. So I think that's kind of a neat problem that goes through excuse me, that goes through incorporation of knowledge from chapter 3 and 4 into this. And yeah, I call this knowledge, but really a lot of this is still just units and unit analysis. I mean, even if you didn't know most of these equations, for example, if you didn't have this equation, you could figure this out just from units. So